I discussed about prime ideals, and few properties of prime ideals. And also I talked about maximal ideals. Maximal ideals. And I have shown the relation between prime ideals and maximal ideals, when a prime ideal becomes a maximal ideal, and under what condition a maximal ideal becomes a prime ideal. So you have seen that if broadly speaking, if I recap this, so if I have any maximal ideal, say a maximal ideal, and if we have say prime ideal here, then when maximal ideal implies prime ideal, what could be the condition on ring? Can anybody be able to say? When a maximal ideal becomes a prime ideal, under what condition on the ring? So the
Commutative
ring,
ring with one.
very good. So it should be commutative ring with one. And we have shown that the converse is not true in general. Okay. So for example, a prime ideal in a commutative ring with one may not be a maximal ideal. For example, in Z, so Z is a commutative ring with one, 0 is a prime ideal, but not a maximal ideal. Okay, so the converse is not true in general. So what could be the extra condition that we should impose over R and maybe the prime ideal, so that every prime ideal having that property under this ring will be a maximal ideal? Can anybody be able to say what could be the extra condition that we impose on R as well as on the prime ideal? Anybody? So it should be integral domain, okay, and prime ideal should be non-zero prime ideal. Non-zero prime ideal. So in integral domain, every non-zero prime ideal becomes a maximal ideal. So see here, except for zero ideal in Z, every prime ideal becomes a maximal ideal. So this part is very important, and every year I mean almost every year you will get some of the questions regarding this maximal ideal and prime ideals. And I have shown you in many cases this zero ideal plays an important role, and many students, they usually miss this condition that zero ideal is there, and they give the wrong answer even though they know almost the complete result. So that's quite important. So in today's class, I will basically discuss more important results, which is related to the irreducible elements and all. So last day also I discussed about prime elements, of a ring. So what do we mean by a prime element of a ring? So as I mentioned in my last class, in whole of my classes, I will assume that the ring is with one. Okay. So the ring is with one, as well as the ring is commutative ring with one. So as I mentioned in my last class that there exists general definition for any arbitrary ring with one, maybe without one. But for the sake of simplicity, we assume that the ring is commutative ring with one. As a result, we'll get some simplicity or some simple uh, condition is there, so that we can check easily whether the ring is, whether some ideal is prime ideal or not. Okay, so what is the definition then of a prime element of a ring? So as I mentioned, let us assume that, let us assume that R be a R be a commutative ring with one. So a non-zero non-unit element. So you understand about what is non-zero and what is non-unit. That means those elements which do not have the inverse, multiplicative inverse. So a non-zero non-unit element P belongs to R is said to be a prime element of R if for all AB belongs to R, P divides AB implies either P divides A or P divides B. So you can understand that's the normal definition of prime number, prime, so prime number, so prime number in natural numbers. So where we usually assume that if P divides implies either P divides A or P divides B. So that's the usual definition of prime numbers or prime integers. So that is being extended here, but here instead of, so n is not certainly a ring, but we can think of this is a z in Z, or even in arbitrary commutative ring with 1, we can have a general definition of an prime element. See, here I am not mentioning this as a prime number, but it becomes an element, prime element. Okay. So there are plenty of such example I discussed in my last class. And in the PID, we have seen that a prime ideal, a non-zero prime ideal basically is generated in a PID, is generated by an prime element, and the converse is also true. So we have seen that theorem in a PID, in a, sorry, PID, principal ideal domain. I have already mentioned what do you mean by principal ideal domain. That means an integral domain in which every ideal is generated by a single element. For example, z plus dot. You can see that any ideal must be of the form nz, where n is an integer. So in a PID, we can write it a prime element, a prime ideal P is generated by, so it has to be non-zero, non-zero prime ideal. That's very important. Non-zero prime ideal P is generated by a prime element of R. So in a PID, a non-zero prime element, prime ideal P is generated by a prime element R. Converse is also true. You can check that this converse is also true. Okay. So try to generalize this for a principal ideal ring, whether the same result happens with principal ideal ring. That means here this is an example of an integral domain, not an I mean this is D means integral domain, and whether the same result is also true for principal ideal ring. That means a commutative ring with 1 in which every ideal is generated by a single element. So here this is a integral domain in which every ideal is generated by a single element. Here just I generalize this concept of integral domain into arbitrary commutative ring with 1. So the question is whether the same result is true for PIR or not. So that you need to check. So can you very quickly give an example of a PIR which is not a PID? Question. An example of a PIR which is not a PID. Can you quickly give me an example, such an example?
Plus dot.
Sorry?
Then Z6 plus dot.
Very good. So Z6 plus dot. So you can very easily understand that since this is a composite number, this cannot be an integral domain, and this is a PID, because what are the ideals here? Can you tell me what are the ideals? All ideals are, this is one ideal, then class 0, class 3, this is an ideal, and then class 0, class 2, class 4, this is an ideal, and then at the end Z6 is an ideal. So this is generated by class 0, this is generated by class 3, this is generated by class 2, and this is generated by class 1. So all the ideas are generated by some single element. So that is why this is an example of a PIR, which is not a PID. So that's quite interesting. So the question is, can you generalize this result in this same result and the converse part with respect to this PIR? So the question also here I can ask you, is the converse true? Is the converse true? So converse of this result. That means if you have some ideal generated by some prime element of R, whether that would be a prime ideal or not in any PIR, okay, or even any PID, whether the same result is true or not. Okay, let us come to some problem which usually appears in some competitive exam.
So one question,
So yes,
sir. In generally, if we know that this is like ZX, we already know ZX is not a PID. We show that. But if we don't know about a integral domain and ask they if this is whether this is a PID or not, then how can we use that?
the question is not clear. Can you please repeat once again?
Like we already know ZX is not PID.
Yes.
So whenever they ask, we already seen the have seen the example, so we conclude that. But if the ring is or integral domain is unknown to us, then what should we do?
Unknown to us means it may happen that you are unable to check whether that is a PIR or
Yeah,
PID.
yeah,
That
yeah, yeah,
is
yeah. PIR is PID. I am more saying about PID.
okay. So that depends actually. So it basically the result states that in a PID or in a PIR the result holds or doesn't hold. So unless you know, suppose you are given that you know that in a commutative group, say finite commutative group can be expressed in some particular way, right? Now, if the question is if you are unable to guess whether this is a commutative group or not, then it would be difficult for you to give the answer. So here also the same thing. It gives you the results tells about if the ring is a PIR or PID, then the result is there. But if you are unable to guess whether that's a PID or PIR, then it would be really difficult for you to give the answer, right? So the result says that it will be only for this kind of ring. So unless you will be able to guess whether this is a PID or PIR, then it would be difficult. Some other result may be useful there. Okay,
Yes, sir.
is it clear? Okay,
Yeah, yeah.
okay. So please try to solve this problem. So is the screen visible to all of you? Okay, it says that let Z125 be the ring of integers modulo 125 under the operation of addition modulo 125 and multiplication modulo 125. If M is the number of maximal ideals of Z12, okay, let me first, in my last class, I have already explained about maximal ideals. So let me once again give a just idea of what does it mean. So again, in my setting, I assume that the ring is with one it's a commutative ring. So suppose R is a commutative ring with one. I say M is a ideal. So we call it when we call it a maximal ideal. So let R be a commutative ring with one, a proper ideal. This is very important. Proper ideal M of R. So this is very important. M cannot be equal to R. Is said to be a maximal ideal of R if there exists no ideal I of M such that M is properly contained in I, which is properly contained in R. That means if you write it pictorially, then you cannot find some ideal I which lies exactly in between M and R. In other words, if you assume that there exists some ideal I which contains M properly, then you need to show that I should be equal to R. That means there exists no ideal in between. For example, if we have Z at our hand, so Z plus dot is a commutative ring with 1. If I consider, say, 7Z, okay, then if I ask you the question, can you find any ideal in between 7 and Z? Then you will find that there exists no such ideal in between Z and 7 which are properly contained. That means you cannot find any such ideal I such that 7Z is properly contained in I, which is properly contained in Z. Okay. Again, if you consider 3Z, 3Z, you can understand that there exists no ideal in between 3Z and Z. That means this is also a maximal ideal, this is also a maximal ideal. That's why we do not call it as maximum ideal, but it's a maximal ideal. Okay. Now, if I ask you this question, then try to answer what would be the answer. Is it visible to all of you? It says that if M is the number of maximal ideals of Z125 and N is the number of non-unit elements of Z125, then what would be the value of M plus N? So it came in some competitive exam. Okay, somebody tell me.
There is
Sir,
only one
3.
maximal ideal, I think.
What is this value? I just want this value, nothing
Sir,
else.
3
First,
have
how much?
3.
Okay, somebody says 3. Okay, let me. Can you please tell me your name? Who told 3?
MD
Huh?
Sariful Mullah. MD
Sariful,
Sariful Mullah.
Sariful says 3. Okay, very good. Then somebody else. It's a calculative one, so you have to put the value. So all of you must prepare for the GATE exam. So GATE happens only once in a year, but unlike, so in case of NET exam, you will get this NET twice in a year, except for say few years, like last year it happened. Otherwise, the normal trend is you will have two NET exam in a same year and only one GATE exam in every year. So I think this question came in some GATE exam. Okay, anybody else?
Sir,
One
26.
is
Okay, somebody says 26. Who said 26? Orko Provo.
Yes, sir.
Okay, 26. Then anybody?
26.
26.
The
Okay,
26.
okay, 26. There are many 26. Okay, dot dot dot. Let's see. Okay, first of all, let us try to find who are the ideals of Z125. So that's the first question. The who are basically the ideals of, so all ideals of Z25. If that is my question, first let us try to find who are basically the all ideals of this. If I ask you a simple question, who are all subgroups of, how many subgroups are there of Z125? How many subgroups are there of Z125? Is the question clear
Number of
to?
divisors of 125.
Okay. Again, see, You are perfectly okay, but my question was how many proper subgroups, how many subgroups are there for Z125? So what you told is perfectly okay, but that's not a number. So you actually, what you told is basically how to calculate. But my point was how many. Now give me the answer. How many?
4 tau
Sir, 4.
5
Okay.
tau
So
25.
is basically 5q, right? So number of positive divisors of this. So we know that 1 is a positive divisor, 5 is a positive divisor, 5 square is a positive divisor, 5 cube. So in general, in the very simple number theoretic course, you must have studied this. If you missed this, you can have a look at my this number theoretic videos. There we have calculated. So this is very important for competitive exam. So the number of positive divisors, if we consider, is this. So 5q is nothing but 3 plus 1, which is 4. Okay. But if I ask you what would be the number of positive divisors of say 7 to the power 4, what would be this value?
20 20
So yes, so this is a multiplicative function. So if you forget it, then either you can read any number theoretic book, or you can very quickly go to the videos on number theory. I have given this lecture for undergraduate students, so you will certainly find this. So as I mentioned, this is 4 and this is 5, so this is 20. Okay, so first of all we check how many subgroups are there of Z125. Now why I am asking you this question, what is the relation between the number of subgroups and the number of ideals of this, number of subgroups of this and number of ideals of this, what is the relation between these two? What is the number of subgroups and number of ideals, what is the relation between them?
Sir, number of ideals less than equal to number of subgroups.
Okay, but in case here, what would be the
Here
relation?
it is equal to.
Yes. So here, in case of Zn, the number of ideals and the number of subgroups and the number of normal subgroups are basically the identical. I mean, they are the same. So here you can understand that there exist exactly 4 ideals of this. Okay. Now the next question is how many maximal, the question was how many maximal ideals, right? How many maximal ideals are there? Okay, how many maximal ideals of this? Now tell me how many maximal ideals are there? So out of which, so this is basically only one, that means Z125. Okay, so so if you consider, so there exist four ideas. Can you tell me quickly what are these ideas? So basically these ideas, one ideal is generated by class 1, one ideal is generated by 5, one ideal is generated by 5 square, one ideal is generated by 5 cube. And what is 5 cube? This is nothing but 0. Okay, so there exists exactly 4. This is nothing but the whole 125, and this is nothing but the 0 ideal, and they are 2. Now out of which, so this cannot be a maximal ideal because this is not a proper ideal. So from the list of this, it cannot be a maximal ideal. Now 0 ideal, in my last class I have already explained that when 0 ideal could be a maximal ideal. So or whether this, in case of, so this is not an integral domain, right? So it has 0 divisor. So in an integral domain we have shown that 0 ideal could be a maximal ideal, but since this is not a integral domain, then you can see that already this is certainly contained in ideal generated by 5. So it can never be a maximal ideal, so this is also gone. Now tell me among which will be the maximal ideal, these two. Which will be the maximal ideals?
Generated by class of 5
Exactly. So
for
this
5
will
square,
be
5
the,
square.
okay, somebody says 5 and somebody says 5 square. Now tell me which one, 5 or 5 square?
Sir, 5.
Sir, 5, 5. Sorry, sir. 5.
Fine.
No,
Okay. So you can understand in this ideal generated by 5, that will certainly contain this one, right? So it will have class 0, class 5, class 25, and then class 50 and so on. So you can see that this is whatever will be here will must also be here. So class 5 square, that means 25 class, is certainly contained in class 5. So this will be the maximal ideal. Okay. So, but here what in my question I asked you what is the number. So if m is the number of maximal ideals, so m value will be 1, and n is the number of non-units of Z125. Mind that this is n is the number of non-units. Okay. Now tell me how many non-unit elements are there. How to
Sir, এটা
calculate?
25,
Sorry,
স্যার সামটা 25 হবে,
whose sum?
m plus n।
Oh, that I don't know, but so you gave how much? 3, right? Your answer was 3.
স্যার এটা
Let's check.
25 হবে।
Okay, you gave 25. Let's see. He has modified his answer and then he says it's 25. Okay, let's check. Now tell me what would be the number of non-units. Mind that here it's given non-units. So how to calculate how many non-units element are there? Somebody?
The
sir,
elements,
total number of elements minus the number of elements whose GCD is 1 with 125.
Very good. So now the question is how to calculate how many numbers are there which are relatively prime to 125. So that we know phi of 125. Now quickly, can somebody be able to tell me what is this value?
So 25.
Okay, this value is 25. Phi
100।
of
125 minus
100.
no. What I am saying
100.
is
100,
this
sir.
value is 5q. Again, if somebody forgets this Euler phi function, please have a look at any number theoretic book, or you can see my videos on number theory. And it says that p to the power n into p to the power n minus 1. That means 125 minus 25. This is 100. Okay. So the number of, this is the number of units in Z125. So how many non-units are there? Non-units are 125 minus 100. This is 25. So the value of n is 25. So value of n is 25. So altogether it should be the value m was 1 and the value of n was 25. So altogether n plus m was 25. Sorry, n plus 20. N was, yeah, n was 25, m was 1, so 26. So 26 was the correct answer. Now it's clear to all of you. Any doubt if you have, please let me know. Okay, so is it done? Good. Now we come to, let's see what extra. Yes, so let's have a look at this. So it came in 2014 June. Okay, I think is the screen clear to all of you? Okay, it says that P and Q are two distinct primes. Then which of these options are correct? And it could be multiple correct. It may be single choice, it could be multiple choice. Okay, now tell me what would be the answer. Say 1, 2, 3, 4 are there. So which one or more answers may be correct? Tell me.
So first one, the first option is definitely wrong.
Okay. So what would be your answer? Just tell me the numbering. 1, 2, 3, 4. Out of which, what would be your answers? Then we'll go for discussion.
Actually, Z by P square Q Z, it is
No,
isomorphic to Z.
just give me the answer. 1, 2, 3, 4. Out of which will be your answer? Then we'll go for the discussion. Quickly, tell
Sir,
me.
is this single option correct?
That I don't know actually. So what I say for NET exam, try to prepare for multiple correct choice. Then certainly it will help you for single correct choice. So just have a look at this question. Whatever will be the correct answer, you have to answer. That's all.
B, option B.
Okay, means 2. Okay, somebody says B. B means 2, right?
Yeah.
Okay, somebody says 2. Okay, let's see. So this is the first option. Then somebody else.
Sir, option 3.
Okay, somebody
Prime
says
ideals.
3.
I have said prime ideals. Okay. I haven't seen prime. I haven't seen prime. No, prime
So
ideals. Just a minute. Just a minute. Option
okay,
two.
okay, so this is option 2. Option 2, you gave the option 2 first, right? So it's okay.
Yeah.
You are with option 2. Okay, let's see. Okay, Aniket,
Yes, sir.
which one would be the answer?
Sir, I'm thinking.
Untik,
Say option 3.
okay, Untik says option 3. Okay, Nikita,
Sir, thinking.
okay, Koilash is there. Koilash,
Sir, three is right. Sir, three is right.
Sir, 3
Z12.
and
Just
4.
take the example.
Sir, I think 3 and 4.
okay, somebody says 3 and 4. Many of you is going for option 3. Let's see. Okay, so first tell me who told option 2. So what was your argument behind
No.
it? And
Actually, I contradict. Z12. Z12 is the contradiction.
okay, so by contradiction you got this answer. How?
Yeah, actually, Z12. If I go for, I have ideal generated by 4. Now, if I do 2 into 2, then that lies on 4, but uh, 2 does not contain 4.
Yes. So then how many? What's about ideal generated by 3? So
Sorry?
he talked ideal. So you talked about Z
12.
12.
Yeah.
Yes. So how many? So you told 2 or 3? I mean, you told option 2, right? 3 distinct.
Option 3. Two,
Oh, you,
did a mistake. I did a mistake here. That's why I
okay.
took him.
Okay.
Basic
Okay, fine.
fundamental mistake.
Sir, I would like
So
to change my answer to option 2.
you would like to go to for option 2, right? Okay.
Yes, sir.
Okay. Give me the argument why you are going for option 2. Option 2 says that it has exactly 3 distinct prime ideas. Okay. Tell
Yes,
me who
sir.
are this
That trivial ideal is one,
trivial ideal?
is a prime ideal.
Which ideal? Trivial ideal means?
The zero ideal, null ideal.
Okay. Then,
Then we can take the ideal generated by say P and the ideal generated by Q.
okay. And tell me, so why zero ideal is a prime maximal ideal here in say
So it is
Z12?
a prime ideal because if AB uh, is in I, then either of them
So
must be zero.
okay, so here in Z12, okay, so class 0 equal to class 6 into class 2 belongs to ideal generated by 0. Now what would be your conclusion? If this is a maximal ideal, then it has to be a prime ideal as well, right? It's a commutative ring with 1. Then what would be your conclusion? So either class 6 will belongs to 0 or class 2 equal to 0, or class 2 belongs to class 0, which is not actually true. So as I just mentioned in our last class, we have already discussed about if this is an integral domain, then only 0 ideal will be a maximal ideal. If this is not, then you cannot talk about, so not maximal ideal, prime ideal. What I told, this if this is a integral domain, then only this would be a prime ideal. But see, in case of here, this is your 0 ideal, and so 0 belongs to 0, but 0 you can write it in this way. If it contains an 0 divisor, so this is not a I mean integral domain. As a result, you cannot write like this. So this is, so you have, suddenly you will have this uh, ideal generated by 2, right? Then how can this be a maximal ideal? Is it clear to you? So again, so what I am going for here is, if we look back here, okay. So the question that was asked was, it has, according to you, you said that it has exactly 3 distinct prime ideals, right? Now what I am saying that, and you say that, okay, in Z p square q, in, sorry, again, so the question that we asked here was this, and you gave this answer. So according to you, it should have 3 distinct prime ideals, right? So let us check. So Z in here, it's Z p square q. You told that the ideal should be ideal generated by 0, ideal generated by P, and ideal generated by Q. But you can understand now very well that this cannot be a maximal ideal, because certainly the ideal 0 is contained in ideal generated by P. It happens if instead of P square Q, if you have only one prime, if it's a field, then it is the result is correct. But if it is not a field, then you cannot say that. In case of a field, since P is a prime, ZP plus dot is a field. So in case of a field, 0 ideal is a maximal ideal. So the question is, in a field, 0 ideal is a maximal ideal. Okay, if I ask you this question, in a commutative ring, if 0 ideal, so okay, commutative ring with 1, if 0 ideal is, so in a commutative ring with 1, if 0 ideal is a maximal ideal, then R is, say in a commutative ring R with 1, if 0 ideal is a maximal ideal, then R is a field. Is it true or false? True or ring R with 1, if 0 ideal is a maximal ideal, then R is a field. Is it true or false? true or false? Is the question clear to you? In a commutative ring R with 1, if 0 ideal is a maximal ideal, then R is a field. Is the statement true or false?
Sir, I
What
guess
would,
true.
In a field,
So true.
in a field,
yes. This one is
there are
done.
only two items.
No, this
There
was
are
is
only two
done.
items.
No, this one is already done. So this in a field, 0 ideal is a maximal ideal. This is always true. Fine. I asked you another question. In a commutative ring R with 1, if 0 ideal is a maximal ideal, then R is a field. Is the converse kind. Is the converse true or false? Or
Sir,
propose
the ring may not be
So
commutative.
ring may not
division
be?
ring.
The
Sorry.
ring may not be commutative.
So I have already given commutative ring with 1. So in a commutative ring R with 1, if 0 ideal is a maximal ideal, then R is a field.
Sir, even then, R can be a simple ring and not be a field.
Okay, give me an example.
Yes, sir, I'm trying to construct one.
Okay, so it's your homework. Just try to convince yourself whether this is true or false. It's a homework. Even I think you will find this in my problem set. If you do it properly, then you will find this in my problem set. So in my problem set, you will certainly find lots of interesting problems which actually appeared in many exams. So don't,
Sir,
yes.
can I say my argument?
Yeah, I think I will do something else. Yes, certainly in my next class, maybe.
Okay,
Uh,
sir.
because if you tell your argument, then others may suffer. They may not try to do it. Okay, so please try to think. And yes, I understand that what you did. So you put one inside, right?
Yes, sir.
Okay. Yeah, that's a correct argument. No, so what we actually try to solve here is basically. So what was the answer? Actual answer? I missed this actual answer, right? What was the actual answer? So what would be this? So the answer will be this will has exactly two distinct prime ideals, because 0 cannot be an, and the question is why not others? Why others? Why you are discarding others? For example, you can understand that p square cannot be a prime ideal here, because cannot be a, so this is a commutative ring with 1, and this is a PIR itself. So in a PIR, every prime ideal is non-zero prime ideal is also a maximal ideal, that you understand. So now the question is why you are not considering any other such ideals, or what is the justification? So here the correspondence theorem plays an important role. So what is the statement for correspondence theorem? Correspondence theorem, what is states? It states that let F from a ring R onto a ring R dashed be an epimorphism. Then there exists a one-to-one correspondence between the ideals of R containing car F and the ideals of R dashed. So sometimes it says that it's a correspondence, it's an inclusion preserving correspondence. Inclusion preserving. inclusion preserving correspondence between the ideals of R containing Karef and the ideals of R dash. What is the meaning of this? So you must read this proof from any standard book, but I am giving you what is the idea behind this, what is the statement, what it says. It says that so there is an epimorphism, that means a homomorphism, and there is a onto mapping. So F is a homomorphism plus onto. Okay. What it says that so this is R and this is R dash. So since this is an onto homomorphism, what you can say that R quotient kernel of F is isomorphic to image. That means R dash. Okay. That we have already seen by using first isomorphism theorem. But it says something more. What it says that there is a one-to-one correspondence. Suppose you take any ideal. So kernel of F, you can understand that kernel of F is an ideal. So kernel of F is here inside R. It says that take any ideal I which contains car F. So I is an ideal of R containing kernel of F. That means car F is contained in I. It says that there is an one-to-one correspondence. Now there is suddenly some ideal here, I dash. It says that there is an one-to-one correspondence between the ideals. Say if you take any ideal which contains kernel F, there must be, you will always find a unique ideal I dash here. That means if you consider the set, say R dash is the set of all ideals of R dash, and if you say R, script R is the set of all ideals containing Karef, then suddenly you will find a mapping which is a bijective mapping from R to R dash. That means if you take any ideal from here which contains Karef, then for that ideal you will always correspond uniquely another ideal I dash from R dash. Other way around, if you take any ideal I dash from here, you will suddenly find some ideal I here which contains Karef. That means there is a correspondence, and this inclusion preserving means if I take any ideal I which is a subset of say I1 is a subset of I2 in R, so both of I1 and I2 contains kernel of F, then it says that inclusion preserving means if I take the function f over this, so f of I1 should also be a subset of f of I2. So that means this is basically an inclusion preserving one-to-one correspondence. Is the statement clear to all of you? Okay. If that statement is clear to all of you, then this statement is very important because many of the questions usually they were asked from this part, but not a direct way, but in an indirect way. For example, here, if you consider this ring Z p square q, then you can very well understand this is nothing but, so this ring is isomorphic to p square q. We have already seen this, okay? Because from Z to, if you define some ring homomorphism from here by f of n equal to class n, then you can see that this is a ring homomorphism, this is an onto homomorphism, and then you can prove this quotient if you have f here, car f, that should be isomorphic to Z p square q. And it happened to be there that kernel of f must be equal to p square q z. So z quotient p square q z is isomorphic to z p square q, right? So these two rings are basically isomorphic. Okay. Just now what we have seen, we have seen that if you have R and if you have R quotient some ideal like this, then suddenly you can define a ring epimorphism like this: A goes to A plus I. You can very easily show that this F is a an epimorphism. So this is an ring epimorphism. So now you can understand that any ideal of this, if you take any ideal of this, and it can be also shown that kernel of F, what can you very quickly tell me what is kernel of F here? If you define like this, what would be the kernel of F?
I.
Yes. So the kernel of F is nothing but this I. And this is known as canonical homomorphism. So this mapping is known as canonical homomorphism. So here suddenly I must be an ideal, otherwise you cannot make it a quotient to get it a ring structure. So I must be an ideal, and if you define like this canonical homomorphism, if you define like this, then suddenly this is an epimorphism, and very easily you can show that kernel of F must be equal to I. Okay. So now try to think about the correspondence theorem. What it says that, so if I draw the image here pictorially, then it will be clear to very easy to understand for you. And here is your R quotient I, and here is your F. Sorry, R, and here is your F. Okay. So kernel of must be here, kernel of F, and it happens that kernel of F equal to I, right? So I is something here, and R is a ring, commutative ring with one, and so on. Now take any ideal of this, take any ideal here. So what would be the form of that ideal? The form of the ideal would be some J quotient I, right? Take any ideal from here. What the correspondence theorem says that, so this is an epimorphism. Just now we have seen this is a canonical homomorphism. So this is an epimorphism. What it says that, take any ideal here, then there must exist a unique ideal here containing this, containing Kf, such that these two ideals are, so for this you must have some ideal here, say J dash, then you need to check what would be this J and so on, whether this J dash will be equal to J, that you need to check. But the correspondence theorem says that for this ideal in R quotient I, there must exist a unique ideal J dash in R such that F of J dash equal to J quotient I. Okay. Now you can very easily understand what could be this J dash and so on. Now, if I ask you now this question, what are all the ideals of Z quotient P square QZ? Now it would be very easy for you to understand. So you basically, all the ideals of this, finding all the ideals of this is equivalent to finding all ideals which contains P square QZ. So you are basically trying to find all ideals of Z which contains P square QZ in Z, because it says that due to one-to-one correspondence using the correspondence theorem. So the question is, how many ideals are there of Z which contains P square Q? Quickly, can you tell me how many ideals of Z are there which contains P square QZ? So P is an ideal which contains this. Q is an ideal which contains this. Sorry, Q, it should be Q. Q is an ideal which contains this. Any other ideals which contains this? Any other ideals?
No.
P square,
P square,
PQ,
then PQ,
and P square Q.
P
itself.
square Q. Any other? Any other ideal? Are these all ideals containing P square QZ or something else left? Somebody?
Sir, sir, the whole
Yes?
ring.
Yes, the whole ring Z. So they are all the ideals of Z which contains P square QZ. Okay. Now the question is, among which, how many of them are the maximal ideals? See, this is a maximal ideal, this is a maximal ideal, this is contained in this is contained in this as well as this, both this is contained in this as well as this, and this is the whole ring, so it cannot be a maximal ideal. So among this, the maximal ideals are basically this ideal and this ideal. So there exist exactly two maximal ideals containing this, and it follows from the correspondence theorem. So I request all of you to have a look at the correspondence theorem from any particular book. You can see my book as well, or any book, Damit Food or Malik Sen Moderation, any book from where you can study the correspondence theorem. But it is very important because whenever you find like this R quotient I kind of thing, always try to use either first isomorphism theorem, and if it is something related to some correspondence with R or some ideal containing kernel of F something, try to always use the correspondence theorem. And this theorem is very important for competitive exam. So people usually they don't find it very useful, but they are really very useful, and the question setters they sometimes do ask questions from here. Okay, now I come to the topic that I actually wanted to teach today, that is the irreducible element, and that is also very important. Why? You will find it maybe in my next class. You will try to get why they are very important. Irreducible element of a commutative ring with one. So that's the basic topic for today. Okay. So first of all, what do you mean by an irreducible element? To understand it, first let us try to define something called associates. Associate of a non-zero element A belongs to R. So R means commutative ring with one. Of a commutative ring R with one. So, okay. So here associate of a non-zero element. What is the meaning of associate of a non-zero element? Okay. So a non-zero element, zero element B belongs to R is said to be an associate of A if there exists a unit U belongs to R such that A equal to U into B. So let us try to understand what is the meaning of associate. So a non-zero element B is said to be an associate of the non-zero element A. So it was already given A was a non-zero element A if there exists a unit U belongs to R such that A equal to UB. So what is this meaning? So what is the meaning of that? Let us try to see. So for example, say if we consider say Z plus dot, this is a commutative ring with 1, and say 3 is my element which is A. Can somebody tell me what would be the associate element for A?
-3.
Okay, anything else? Minus 3 is the correct answer. Now the question is
Multiple of 3.
sorry.
Multiple of 3. 6, 9, 11,
Okay.
12.
So, okay, you said that 6. Let's check whether 6. So if we consider 6 to be my B, then tell me in Z what would be 3 equal to this unit. Give me some unit that should be equal to 6. Give me some unit from Z which will give you this equal to 6 in Z. Okay, those who told me, uh, can you tell me what would be this unit? Okay, so the first idea is what are the units of Z plus dot? Can somebody tell me what are the units of Z plus dot?
So plus minus
Sir,
1.
1 and minus 1.
1 and minus 1. So they are the only units of Z plus dot. Okay, so you can either put 1 or minus 1 here, but there exists no such units here in Z which will make you this equal to 6. That means 6 can never be an associate of 3. So your answer is not correct. Okay, but it was a good try. Okay, let's see. Then somebody, Nikita, told that it's minus 3 is an associate of 3. Now my question is minus 3 the only associate of 3? True or false? Is minus 3
3 is also
the only associate of 3? True or false? True or false?
Sir,
3 is also an
Exactly.
3
So
হবে
this
স্যার।
is false. Yes. So it's not 3, it's minus 3, but it's also, I mean, it's minus 3, of course, an element, but 3 is must be also, because if you put it here, if you put it here, this, if you instead of 6, if you put it here 3 or minus 3, then suddenly you can do this. If you put it here, then you can have 1 or minus 1. That means you can put it, uh, if you put it like this, then minus 3 can also be an element, as well as if you put 1 here, then it will also be equal to 3. That means the associates of 3 is plus minus 3. Now if I consider here in another ring, if I consider in Zi, what are the associates, or what are the units of Zi? Units of Zi. Can somebody tell me quickly what are the units of Zi? And also in Z root 5I, what are the units of?
1 minus 1 I minus I.
Okay, in case of, so in, he says 1 minus 1 I minus I. Good. And in here, what are the units of this? So 1 minus 1 will certainly be there. Anything else
No.
that you need to check? So if take any element A plus IB, if some units are there, then the units must look like some, say, U plus IV, and that must be, so if this is an unit, so if this is an unit, suppose the unit should look like this. If this is an unit, then its multiplicative inverse exists. So if I, then there must exist some E A plus IB. If you make it a product, then it should be equal to 1. Now check what could be this value of U and V. Then you will find that they are the only solution for this. So in Z root 5I, 1 and minus 1 are the only units of this. Now if I consider Fx, where F is a field, so it's a polynomial ring over the field F. Now tell me who are the units of fx. Who are the units of fx?
So F এর unit
So the only units are units of f. So who are the units of f? So exactly this. Yes, you are right. All the units of f will be the units of fx. And what are the units of f? All non-zero elements of f will be the units of f, because f is a field. Okay, so that's very important. Now, because why this is important? Because I need to give the proper definition for irreducible elements. Now the irreducible element definition will be very clear to us. Okay, so irreducible element. So this is irreducible element. So again, as I mentioned, I consider R to be a commutative ring with 1. So let R be a commutative ring with 1. A non-zero, just like prime element, non-zero non-unit element P belongs to R is said to to be a be an irreducible element of R if for all AB belongs to R, P equal to AB implies either A is a unit or B is a unit in R. So what it says, let R be a commutative ring with 1, a non-zero non-unit. This is very important. It has to be a non-zero element. It has to be a non-unit element. P of R is said to be an irreducible element of R if for all AB belongs to R, P equal to AB implies either A is a unit or B is a unit in R. Okay. So is the definition clear? Okay. So let us try to see in Z. So in Z plus dot, let us try to check whether 3 is an irreducible element or not. Irreducible element. Why? Take 3 equal to any form, say A into B. Then you can understand how can you write 3. 3 can be written as 3 into 1, or you can write minus 1 into minus 3, or 1 into 3, or minus 3 into minus 1. Except for this, can you write 3 anyway in terms of A and B, product of these two numbers? And you can see that in all of them, so it has to be like if you miss any one of them, you have to write 3 as a product of all possible way, and if you miss any one of them, such that some of them should be, at least one of them should be unit. So here what it says that 1 is a unit, so you are done. Minus 1 is a unit, so you are done here. Here 1 is a unit, you are done. Here minus 1 is a unit, so you are done. So in all the cases, you can see that if I write like this A into B, then either A is a unit or B is a unit. Okay, so let me check whether 1 is irreducible or not. 1 is irreducible or not. So if it is not irreducible, we call it reducible. Okay, so question is, tell me 1 is irreducible or reducible? So I or R? Tell me whether it is I means irreducible, R means reducible. R is I, so one is reducible or irreducible? I or R? Quickly.
One is a unit here, so we cannot tell that.
Okay, that means it's not irreducible. If it is not irreducible, then it must be R. So one is out of the question. Okay, good. So good observation. So it has to be non-zero, non-unit. Okay. So in Z, if P is a prime element, then P is irreducible. Is it true or false?
True.
True or false? Okay, somebody says true. Everybody convinced? So in Z, prime and irreducible elements, they coincide. Now the question is it true really for all commutative ring with one, where this prime elements and irreducible elements, they do coincide? So what would be your guess? What would be your guess? So in a commutative ring with one, what is the condition that one should take so that we can make a difference between prime element as well as irreducible elements? Okay, so first try to think about in a commutative ring with one. So let's see, let R be a commutative ring with one, be a commutative ring with one. Let P be a prime element of R, then P is irreducible. True or false? What is your guess? What is your guess? What is your guess? So I have taken just a commutative ring with one. Z is a commutative ring with one, and prime element is an irreducible element. You say that it is true. Now I am, instead of ring Z, I just take arbitrary commutative ring with one, and P is a prime element. Okay, let's see Z6 plus dot. So this is a commutative ring with one. What's about class 3? Okay, question, is class 3 a prime element of Z6 plus dot? Is class 3 a prime element of Z6 plus dot? True or false? In my last class, I think I did it. Is it true or false?
True, sir.
False.
True. Okay, somebody says true. In my last class, did I completed that? Okay, let's see. So I think in my last class I made this. Anyway, I'll just again doing the same. Okay. So somebody says true. So if it is true, then let AB belongs to Z6 such that, what is the definition of prime? P divides class A into class B, right? I should get either P divides class A or P divides class B. So here, okay, it's P equal to 3, class 3. That means class 3 divides class AB. That means there exists some class C. I have already defined in my last class what does this division means, such that AB equal to 3 into class C. That implies 6 divides AB minus 3C. I think if you remember in my last class, I did all these things. That implies 3 divides AB minus 3C. So if 3 divides this and 3 divides this part, then suddenly 3 divides AB. Now remember this A, B and 3, all of them they are from integers. And 3 is a prime number. What is the meaning? That implies either 3 divides A, either 3 divides A or 3 divides B. Now if you transfer this into Z6, then suddenly it will have either class 3 divides class A or class 3 divides class B. So that implies class 3 is a prime element. Now the question is whether class 3 is an irreducible element or not. Question: is class 3 an irreducible element? Of Z6? What would be your answer? True or false?
So false.
Okay, why?
So 3 equals to 3.3
Very good. So
and 3 is
class 3 equal
negative 1.
to 3 into 3 in Z6. So this belongs to, so 3 equal to this, and if 3 would be an irreducible element, then that should imply either 3 is a unit or 3 is a unit. But in Z6, 3 is not a unit. But in Z6, class 3 is not a unit. Hence, class 3 is not irreducible in Z6. So what we get? We get that in a commutative ring with one prime element may not imply irreducibility. So what we had here, we had prime element, prime element. Here we have irreducible element. What we had, prime element may not imply irreducible element in commutative ring with one. Okay. So what extra condition that we must impose upon commutative ring with one so that prime element will imply irreducible element? So that's the next question. Okay, so let us check in an integral domain what happens. See, J in Z we have seen already that prime element implies irreducible element, and Z is an integral domain. So let us try to have formulate our theorem like this theorem, and let us try to check whether the theorem is true or false. In an integral domain, every prime element is irreducible. Okay, let us try to prove this. So let R be an integral domain and P belongs to R, be a prime element of R. Then P is non-zero and non-unit and non-unit. So that we require for the definition of irreducible element, it has to be non-zero and non-unit. From the definition of prime element, it must be non-zero and non-unit. So The first step for irreducibility is done. Now what we need to check? So let AB belongs to R such that P equal to AB. Then what we need to show? Either A is a unit or B is a unit. So that we need to show, right? Now tell me somebody how to proceed. I have given you enough ample of hints. Now tell me somebody how to proceed. So I need to show that either A is a unit or B is a unit. Okay, now the proof is not very difficult. Just try to think how to proceed.
Sir, integral domain does not contain zero divisor,
Very good.
and P is not non-zero.
Yes.
Then either
So just try to remember that you need to use this hypothesis is P is prime, right?
yes,
So it's given that P is prime. So you need to use the property of prime element to show that either A is a unit or B is a unit. Okay, tell me now.
and prime element, then either P divides A or P divides B.
Very good. Let us can you please write it in a formal way? So as P equal to AB, that implies P divides AB. Okay, since this is the ring with one, so we can write it like this. Okay, as P is a prime element, as P is a prime element of R, either P divides A or P divides B, then good, then, but you need to show that one of them must be unit. Okay, then you're right.
So suppose P divides A,
Okay,
then there exists C belongs to R such that A equals to PC.
suppose P divides A. Okay, then as I mentioned in my last class, the definition of division means then there exists some C belongs to R such that A equal to PC. Very good.
Now put the value of A in P equal to AB.
Then
Put the value of A in
very
there.
good. Okay, then P equal to AB implies P equal to PCB. Okay, that implies you can
Unit.
make a common 1 minus CB. Okay, equal to 0. Now tell me,
P is non-zero and it is an integral domain.
yes. So
So
as P is non-zero and R is an integral domain, so 1 minus CB must be equal to 0. That implies CB equal to 1. So this is a commutative ring. That's why BC is also equal to 1. What it implies? That implies B is a unit. Similar, by similar argument, you can show that. So where you use, suppose this divides this, by similar argument, we can show that if P divides B, then A is a unit. So what is your conclusion? That implies P is an irreducible element of R. Is it clear to all of you? So is in an integral domain, what it says that in an integral domain, every prime element is irreducible. Okay, the proof was very easy. Now a simple question may be asked, is the converse true? That means in an integral domain, is an irreducible element be a prime element? So the question is, is the converse true? Oh, okay. Let me save this file. So today is ring. Okay, let me have some new. Yes. So the question is the converse true? That is, in an integral domain, is every irreducible element be prime? True or false? What is your guess?
So my guess is false.
Okay, your guess is false. Good. How? Can you justify?
So I just try to construct an example.
Okay, good. Okay, I'm giving you some hints. Consider z root 5 I. Okay, and consider 3 and 6. So 3 divides 6. Okay, so what do you need to show? In, so no doubt this is an integral domain. And what are the units? Just we have seen that 1 and -1 are the only units here. Okay, and I have taken 3 and 6. Now I want to check whether 3 is prime irreducible or not. Okay, so first let us try to check whether 3 is prime or not. So what do you need? So 3 divides 6. And how can you write 6? There are many ways to write, right? So you can write it 6 into 1, 1 into 6, then 2 into 3, then -2 into -3, then suddenly 3 into 2, -3 into -2. Any other way that you can write it? Any other way?
1 plus root 5i into 1 minus root 5i.
Very good. 1 plus root 5i, 1 minus root 5i, or the other way around. I just not writing, say here also -1 into -6 and so on. So this is very crucial. That's why what I told you, see here either this is unit or this is unit. So here this is unit, you are done. Here this is unit. But here you can see that uh, no. So what we are trying to check whether this is a prime or not, right? So 3 divides 6, that means 3 divides AB, 6 into 1, either 3 divides 6 or 3 divide 1. So here 3 divides 6, so you are done here. Here also 3 divides 6, you are done here. Here 3 divides 3, you are done here. Here 3 divides -3, you are done. Here also you are done. Here also you are done. So you are done almost everywhere. But as I mentioned, it should be in all. That's why for all AB belongs to R, wherever you can write 6 in that way. So you can write 6 also in that way. Now, if 3 divides one of it, then you are basically done because you have already exhausted all the possibilities. Now try to check whether 3 divides 1 plus root 5I. What is your guess? Do it satisfied or not? True or false? What is your guess? Okay, can someone, yeah, true or false?
False.
Okay, somebody says false. Okay, how to check it's false? How do you say that it's false?
So if 3 divides 1 plus root 5I, then we can have some a plus b root 5I belongs
Very
to
good.
z root 5I, such that 1
So
plus root 5I equal to 3 into a plus b root 5I.
very good. Root 5I. Then there exists some element belongs to z root 5I. That means then there must exist some a plus root 5I into b belongs to z root 5I, such that 1 plus root 5I must be equal to 3 into a plus root 5IB. Now then, what to do then?
Then we
That
should compare the real and imaginary parts.
yes. And what happened here? That implies
A
that
equal
equal to 1. A equal to 1 by 3
doesn't belongs to z.
does not belongs to Z. A contradiction. That's why if this happens, then you will get a contradiction. That implies 3 does not divide 1 plus root 5I. By similar argument, you can also show that 3 does not divide 1 minus root 5I as well. So 3 divides whole thing, but 3 neither divides this nor this. What would be your conclusion? That implies 3 is not prime in Z root 5I. Okay, so that's very important observation. So the question is whether 3 is irreducible or not. So whether 3 is irreducible or not. So what is our aim? Our aim is to check in an integral domain every irreducible element is prime. It is true or false. So if we have if we find that 3 is an irreducible element and z root 5I is an integral domain, then will be some at some conclusion. Like if we be able to show that 3 is an irreducible element in z root 5I, then that irreducible element will not imply automatically that 3 is a prime element. That means whatever you mentioned earlier it's false will be justified. So now our claim is 3 is an irreducible element. Claim here 3 is an irreducible element in z root 5I. Okay, how to prove that? So as usual, let a plus root 5IB and c plus root 5ID belongs to z root 5I, such that 3 equal to a plus root 5IB and c plus root 5ID. What you need to show? You need to show either this is a unit or this is a unit. This is a very common technique of doing this. Take 3 bar, which is suddenly equal to a conjugate, complex conjugate, that equal to a minus root 5 IB, c minus root 5 ID. Now, if you make a product of this, what you will get? You will get 9 equal to, here you will get a square plus 5 b square, and here you get c square plus 5 d square. Now see that all of them are the square, sum of squares elements, positive square. So these values, none of these values can be negative. Okay, all of them should be greater than equal to 0, and its value is 9. So what could be this distribution, either this is 3 into 3 or this is equal to, so what would be your thing? This is could be 9 into 1 or 1 into 9. So none of them will be negative, right? Anything else in z root 5I, you cannot make anything else. Okay, that are the only possibilities. Now if you have, that means case 1, if you take this one, if you have case 1 as case 1, say a square plus 5 b square equal to 3, c square plus 5 d square equal to 3. Then can you find some a and b which are integers such that a square plus 5b square equal to 3, or similarly here? So you can see that no such AB belongs to Z exist such that this happen. Now case 2. That means this case is not possible. Now case 2, whether this is possible or not. So a square plus 5b square equal to 9, c square plus 5 d square equal to 1. Can you find some a b c d such that this is satisfied? Can you quickly say me the value of a, b,
Sir, 2,
c?
2, 1.
Value of a
Yes,
a
sir.
is
Sir, A2,
a2,
B1,
b1,
C1,
c1,
D0.
d0. Okay, can it also be a equal to plus minus 3, b equal to 0, c equal to 1, plus minus 1 in fact? Here also you can put plus minus 1, d equal to 0. In any case, if you write it like this, so this part you can have like this, but this part suddenly d has to be 0, and in that case this part will be either plus 1 or minus 1. Okay, that means if you write like this, 9 equal to a plus root 5 I b c my plus root 5 I d, then suddenly this value is 9 and this value has to be plus minus 1. So that means in that case, if you have like this, so you can arrange depending on the situation whether this is plus 1 or minus 1. Okay, so if it is plus 1 or minus 1, if you take this case, then also you'll find one of them, this part corresponding to that, that will be an unit. And this I have already shown you that this part cannot happen. So you had only these two parts, and among these two parts, either corresponding to this part is unit or corresponding to this part is unit. So your conclusion will be 3 is an irreducible element. In Z root 5 I. So what was our conclusion? Conclusion was in an integral domain. So the conclusion here is, so what we had seen already, so integral, so prime element will be integral domain will imply irreducible element. And now we have seen that if it is integral domain, then this relation may not hold. Now the extra condition that we should impose upon integral domain, that will give us the irreducible element should be a prime element. So that theorem states that in a PID or PIR even, so in a PIR, okay, let us PID, okay, let us put PIR, every irreducible element is prime. Okay, let us try to prove. So if this happens, if this happens, if in a PIR, we need to check whether this is PIR or PID. If it is, if somebody could able to find in a PIR this statement is false, then suddenly he needs to go to PID. So first try to prove it for PIR, and then if it fails, then you should put some extra condition that it should be PID. Suppose this is done for PID, then what would be your conclusion? I am saying that this is done for PID. You need to check whether this is true for PIR as well. Then what would be your conclusion? Your conclusion will be prime if and only if maximal, sorry, if and only if irreducible, so prime element, if and only if irreducible element were in PID. So in a PID, every prime element and irreducible element they coincide. As you understand, in case of Z, it happened. So all the prime elements and irreducible elements are exactly the same, but that is certainly not true for any arbitrary ring. Clear? Up to this, it's clear? Okay, now what I'm saying that if you find that this may be a little confusing or too much results are involved, just try to picturize these things. So if you write in this diagram manner, then it will be easier for you to understand, and here you just give the example, then that would be easier for you to remember. Otherwise you may think that okay, sometimes I am saying irreducible, sometimes I am saying prime, and in a PID sometimes it's an integral domain. It's too much, very closely related results, but they are not exactly the same. So there is no doubt that it will create some confusion, but try to give the proof of this. If you go for the proof of this as your homework, then you will remember all these results. Unless you do it formally, you won't be able to remember. You cannot memorize all of them. You just try to think for simple things like z root 5i, or then polynomial ring and etc. Then you will certainly find it easier to remember. Otherwise you will basically lost, and as you understand, the questions that are asked are very nearby questions that you may miss it. That's why it's very important to do some problems. I have given you enough problem in my problem sheet, or you can go to the exercise of any standard book, then you will get all the results. Okay, so now what we am going to do is basically very important result for any competitive exam. The theorem says that, say let R be a PIR which is not an, which is not so let Rx, okay, let R be a PIR which is not a field. Can you give an example of a PIR which is not a field quickly?
6, hit 6.
Z6. Okay, so Z6 is an example of such. So this is an example. Then uh, then the ideal generated by this, where P is an irreducible element, is what do you say? What can you tell about this? Is a, this is a maximal or prime ideal? This is a, what ideal should I write? Maximal or prime? So just now we have made it. Okay, let us try to do. So recall few results. So just now what we have mentioned, in a PIR, every irreducible element is prime, right? In a PIR, every irreducible element is prime. So this is irreducible element. So it becomes prime. In an now, okay, let me make it PID. Okay, then that would be maybe easier for you to. Now, if I have in, if this is integral domain, and if I this is a PID, then the prime ideal, what it generates? It generates the prime, the ideal generated by prime element becomes prime ideal. So this is prime ideal, and in a PID, every prime ideal is a maximal ideal. So is a maximal as well as prime ideals, ideal of R. So that's very interesting result. In a PIR, sorry, in a PID, let it be PID, which is not a field. If you consider any irreducible element, and if you consider any ideal generated by that irreducible element, then certainly that will be a maximal ideal as well as the prime ideal. So that's very interesting and important result. Okay, so is the statement clear to all of you? Is the statement clear to all of you? Any doubt or any question till now? So in a PID, which is not a field, any ideal generated by some irreducible element must be a maximal element. And as you know that in a maximal element, maximal ideal, it has to be a prime ideal in a commutative ring. So it's a PID, so it must be a commutative ring. So we are done basically. So can somebody be able to prove this up to this? Prime is automatic. Can you prove that? So this is not an example of a PI. Can you give an example of a PID which is not a field? So this is PIR but not PID. Can you give an example of a PID which is not
Actually,
a field?
actually, Rx polynomial over the real field, that will not be a field, but PID.
Okay, good. Rx. Z also, right? Okay, good. Now can somebody be tell me how to prove this? Okay, let us have a look. The proof is very simple. What we need to show, that we need to show this is a maximal ideal, right? Okay, so what we need to check basically, so this is my R and this is the ideal generated by P, where given that P is an irreducible element. What I need to show, this is a maximal ideal. What I do, I'll give just basically simple an ideal. So there are plenty of ways to do that. Simple way would be the by using the previous result. So P is irreducible. In a PID, irreducible implies prime, and in a PID, the ideal generated by an prime element will be a prime ideal, and in a PID or in a commutative ring with one prime, sorry, in a PID, prime ideal will imply the maximal ideal. So that's the way that all the using all the results that we have studied till now, we will be able to prove it indirect way. Now let us try to prove it in a direct way. That means we have assumed that P is an ideal and we need to show that P is a maximal ideal. So let J be another ideal, be an ideal of R such that ideal generated by P is properly contained in J is a subset of R. Subset of, sorry, the normal R, the subset of R. What is my claim? Since I need to show that this is a maximal ideal, what I am going to show, this must be equal to R. So claim is J must be equal to my R. Okay. So what is given? So the given condition is R is my PID. Okay. That means all the ideals must be generated by a single element. So as J is an ideal of R, and R is a PID, J must also be generated by a single element. So let J is generated by a single element A. Okay. So why this is so? As R is a PID and J is an ideal of R. Okay, that's why. Okay. Now what is happening here? So what I need to show? Can somebody be able to show what we need to show? We need to show that J is a this P is a maximal ideal of this. Okay, now P must be belongs to P, ideal generated by P, and that is contained in properly contained in ideal generated by A, which is nothing but J. What does it mean? That means P must be belongs to ideal generated by A. What is the definition then? Then by the definition, what is the element looks like? The elements looks like R into A, such that R belongs to R. That implies since P belongs to this, so P must be equal to some A into B for some B belongs to R, or you can write it B into A, and it's a commutative, so A into B, simple way, for some B belongs to R. Now what is your idea? Now tell me what you are going to use. What is given? P is an irreducible element. Now you are basically within the track. As P is irreducible, either P either A is a unit or B is a unit, right? Now can A be an unit?
Sir, if A is an unit, then the J is the whole ring.
Yes. So if A is a unit, then you can understand that J equal to whole R. So then we are done basically. If B is a unit, if B is a unit, then what will happen? Then what will happen?
Then the ideal generated by P will not be properly contained in J.
Very good. How can you say that? If B is a unit, then we have P equal to AB implies A equal to B inverse P, because B is a unit, so you can have inverse, and that belongs to P, right? That implies A is an element which generates J. That implies the ideal generated by A should be a subset of ideal generated by P. That means J is a subset of P. What does it mean? What you assumed here? You assume that it was the just other way around, but here you will get this. So what is your conclusion? So you cannot have, so this is a contradiction. So what do you have? A must be a unit. Be a unit. And in that case, then J must be equal to R. And J must be equal to R. That was your claim, because I want to show that J must be equal to R. That was my claim. What was my claim? That if I can show that J equal to R, basically we are done, because if some J is here, then that J must be equal to R. That means there exists no such J here. That was my claim, and we have proved it. That implies, what it implies? It says that this is a maximal ideal of R. And this results will be very useful for many of the questions that are being asked. So in this class, we have discussed very interesting points. And in my next class, I will basically go for many of the problems that were asked in many of the competitive exams. So please have a look at the polynomial rings. So in the next class, I will go for the polynomial rings and irreducible polynomials. That is one of the most important chapters in ring theory, because that will be useful for your finite field construction as well as Jordan canonical form. When we'll go for Jordan canonical form in your next semester or next on, then this things will be very much useful. And if you look at the question papers from NBHM or NET or GATE, you will find at least one or two questions from this irreducibility of polynomials, the relation between irreducibility of polynomials as well as the maximal ideal, prime ideal, and so on. So that will be very important. So in my next class, I will do lots of problem. So please have a look at all my previous videos. That will be helpful for you. Last video was very important. This video is also very important. Based on these two topics and previously done results, I will go for